IE41 virus. Transportation model. The transportation model is a special case of the LP that deals with the shipping a quantity from a source to a destination. In most cases, the objective of this problem is to minimize the costs associated with shipping the supply from the different sources to satisfy the demand for each destination. We define the following terms. The sources and destinations are each represented by a node. Each source node and destination node are connected by an arc. Each arc is associated by the shipping cost per unit transferred from the source to the destination. In formulating the transportation model, we let Xij be equal to the number of units to be shipped from the source I to destination j. Cij is equal to the cost associated with shipping a unit from source I to destination j. Si will be equal to the total supply of units available in source I, and dj is equal to the total demand of units needed in destination j. Minimize the following. Subject to the supply constraints, the demand constraints, and the non-negativity constraint. The supply constraints ensure that the number of units shipped from source I does not exceed the total available supply in source I. Similarly, the demand constraints ensure that the number of units shipped to destination j satisfies the total demand in destination j. Usually, it is preferred that the transportation model is balanced in which the total supply equals the total demand as it becomes easier to solve. Here, the available supply from all sources I exactly meets the demand of all destinations j. The supply and demand constraints can then be shown as the supply constraints and the demand constraints. To better understand the concept, let us consider the following problem. A certain distribution firm is to supply goods to 3 different supermarkets, A, B, and C. The goods to be delivered may come from 3 separate warehouses, X, Y, and Z. The following diagram shows the amount of goods that can be supplied from the warehouses and must be delivered to the supermarkets, as well as the corresponding transportation costs due to distances between sources and the destination. How should the firm plan the distribution of goods to minimize the total cost? Before we formulate this problem, notice how the total supply of 900 units does not equal the total demand of 700 units. In this case, we place a dummy node as a destination that can accommodate the excess supply. The shipping cost from each warehouse to this dummy node is 0, since we are not actually shipping anything. Note that this shipping cost may be non-zero depending on the situation, and that we may place a dummy source node if there is excess demand instead. Following the notation we used earlier, we formulate this LP. Minimize z is equal to 50x xa plus 75x xb plus 60x xc plus 45 xya plus 80x yb plus 70x yc plus 40x za plus 65x zb plus 50x zc, subject to the supply constraints xxa plus xxb plus xxc plus xxd is equal to 300, xya plus xyb plus xyc plus xyd is equal to 200, xza plus xzb plus xzc plus xzd is equal to 400. The demand constraints xxa plus xya plus xza is equal to 100, xxb plus xyb plus xzb is equal to 350, xxc plus xyc plus xzc is equal to 250, xxd plus xyd plus xzd is equal to 200, and the non-negativity constraints xxa, xxb, xxc, xxd, xya, xyb, xyc, xyd, xza, xzb, xzc, and xzd are all greater than or equal to 0. While it is possible to solve this LP using the simplex algorithm, doing so will be tedious as many artificial variables will need to be generated. A simpler approach would be to use the transportation simplex. For this, we define the transportation tableau. Translating our problem to this tableau, we have... Before we can perform the transportation simplex, we need to first find an initial feasible basic solution. Remember that in the simplex method, we usually assign the slack variables of each constraint as basic initially and move across the feasible region from there. Similarly, we find a starting solution for the transportation LP and move across the feasible region until the optimum is reached. However, since the transportation tableau does not consider slack variables, we assign initial values to the decision variables instead. There are three methods in finding a starting solution for the transportation model of the LP. The first method is the northwest corner method. As the name implies, we allocate as many units as possible to the northwest element of the tableau and adjust the supply and demand corresponding to the element by subtracting the allocated quantity. We demonstrate this with our problem. The northwest element of our tableau is XXA with a per unit shipping cost of 50 pesos. The available supply of warehouse X is 300 units, while the demand of supermarket A is 100 units. Therefore, we allocate the smaller of the two, which is 100 units. We then adjust the supply of warehouse X to 200 units and the demand of supermarket A to 0 units. Since the demand of supermarket A is satisfied, we can cross out this column. If the supply of a warehouse is diminished instead, we cross out that row since it cannot provide to other supermarkets anymore. In the case of ties, we choose which to cross out arbitrarily. Going back to the problem, the next northwest element is XXB, with per unit shipping cost of 75 pesos. We repeat the procedure again and allocate as much as possible. The resulting tableau would be... Notice how we adjusted the demand and supply of supermarket B and warehouse X, respectively, and how we crossed out the row of warehouse X. If we do this repeatedly, we will arrive at this final tableau. Notice that the total quantity shipped will only be up to the value of the total supply or total demand. Remember that the transportation model is always balanced. Hence, one constraint will always be redundant. If we have m supply constraints and n demand constraints, we can only have m plus n minus 1 basic variables at a time. Note that it is possible to assign one basic variable as 0 to achieve this, just like in the simplex and dual simplex algorithms. Given our starting solution, our current objective function value is 50 pesos times 100 plus 75 pesos times 200 plus 80 pesos times 150 plus 70 pesos times 50 plus 50 pesos times 200 plus 0 pesos times 200 is equal to 45,500 pesos. The next method is the least cost method. It is very similar to the northwest corner method, except we allocate as much as possible to the element with the least shipping cost instead of the northwest element. All other procedures, such as those regarding the crossing out rows or columns and breaking ties, remain the same. In our problem, we have three elements that can be our potential basic variable, all with a per unit shipping cost of 0 pesos to be the dummy node. Here we can choose arbitrarily. For example, let us choose to allocate X, XD. The resulting tableau would look like this. The next element with the least cost would be XZA with a per unit shipping cost of 40 pesos. Doing the same procedure, we have the following tableau. Repeating this algorithm, we have our final tableau as... The starting value of our objective function would then be 0 pesos times 200 plus 40 pesos times 100 plus 50 pesos times 250 plus 65 pesos times 50 plus 75 pesos times 100 plus 80 pesos times 200 is equal to 43,250 pesos. The last technique is the Vogel approximation method, commonly called VAM. This method attempts to find a good starting solution by assigning a penalty to each row and column. This penalty is determined by subtracting the smallest cost in the row or column from the next smallest cost in the same row or column. We then identify the row or column with the largest penalty and allocate as much as possible to the element with the least cost in that row or column. In case of ties with the largest penalty, we can choose arbitrarily. Let us demonstrate this in our problem. The penalty for the row of warehouse X is taken to be the smallest cost 0 subtracted from the next smallest cost 50. The resulting penalty would then be 50. If we do this for all the rows and columns, we can see that the largest penalty comes from the row of warehouse X. We then allocate as much as possible to the element in warehouse X with the least cost, which is XXD, and cross out the column of the dummy supermarket D since its demand has now been satisfied. We now repeat the procedure and measure the penalty for each row and column. Notice that since we crossed out column D, the rows of warehouses X, Z, and Y would now have 3 elements each, and the penalties would change as sworn. Notice how the penalty of warehouse X changed from 50 to 60 minus 50, which is equal to 10. Since the largest penalty is in warehouse Y, we allocate as much as possible to the element X, Y, A, with the least costs 45. We then cross out the column of supermarket A. We repeat this procedure until only one row or column remains uncrossed out. From there, we apply the least cost method. Our starting tableau would be as follows. The starting objective function value with this method would be 0 times 200 plus 45 pesos times 100 plus 50 pesos times 250 plus 65 pesos times 150 plus 75 pesos times 100 plus 80 times 100, which is equal to 42,250. If you've noticed, the starting value of the objective function decreased as we discussed the 3 methods. In general, VAM produces the best starting solution in the sense of the smallest objective function value of the 3 different methods, followed by the least cost method and the northwest corner method. While each method may result in a different starting solution, the technique in optimizing this value would still be the same. A better starting solution just has a higher chance of needing fewer iterations to be optimized. In each iteration, the entering variable must first be determined. Due to the nature of the transportation tableau, we can use a simple method for this called the method of multipliers. We associate a multiplier u sub I for each row and y sub I for each column of the tableau such that for each basic variable x sub ij, the following condition is satisfied. ui plus vi is equal to cij. By convention, we set u1 is equal to 0. Let us demonstrate the method of multipliers in our problem. We will use the starting solution resulting from VAM. Notice that we use ux instead of ui to be 0. Since ux is equal to 0, VB and VD must be 75 and 0 respectively, in order for the basic variable condition to hold. Since YB is equal to 75, UY and UZ must be 5 and negative 10 respectively, since UY is equal to 5 and VA must be equal to 40. Finally, since UZ is equal to negative 10, VC must be equal to 60. The next step is to solve for the quantity ui plus vj minus cij for each non-basic element. The values that will result from this would be the iteration value of each decision variable in the 0 of the simplex tableau. Note that we can neglect solving this quantity for basic variables since it will just always result to 0. Since we are dealing with a minimization problem, we let the decision variable with the most positive multipliers minus cost value be the entering variable. xyd is the entering variable. We now perform the transportation simplex. We first assign non-negative value of theta to xyd. Since we added the value to xyd, other basic variables must change in value, with one leaving the tableau, so that the supply and demand constraints remain satisfied. To do this, we move across the tableau in a loop, in which the entering variable is both the starting and ending point. We can alternately move horizontal in a row and vertically in a column, or vice versa, making sure that the ending point of each movement or each corner point of the loop is a basic variable. In each movement from the entering variable, we alternately subtract and add theta to the basic variable. To clarify this procedure, we demonstrate using our tableau. After adding theta to xyd, we can either move up to xxd or left to either xya or xyb. Suppose we move left. If we move to xya, we can no longer move up or down since there are no basic variables above or below xya. We then move to xyb and subtract theta from it. From there, we can either move up to xxb or down to xzr. Suppose we can move down to xzr this time. From there, we are forced to move right towards xzc, but from xzc, we can no longer move to another basic variable in order to close the loop. This means that we can only move up to xxb from xxb. We then add theta to xxb. From xxb, we can only move right towards xxd and subtract theta from it before we go back to xyd and close the loop. Note that the loop does not necessarily have to be a quadrilateral and that it may cross itself. What matters is that each point corner is a basic variable and the loop be closed. We now determine the maximum value of theta in which all constraints can be satisfied. By alternating the solution and addition of theta from the entering table, we ensure that the supply and demand constraints are satisfied. We now check for the non-negativity constraint. Notice that this only affects terms wherein we subtracted theta from. These basic variables must satisfy the following conditions. xxd is equal to 200 minus theta is greater than or equal to 0. xyb is equal to 100 minus theta is greater than or equal to 0. Getting the intersection of the two equations, the maximum possible value of theta is 100. We redraw our table to reflect the changes. Getting the intersection of the two equations, the maximum possible value of theta is 100. We redraw our tableau to reflect the changes. Notice that xyb became the leaving variable when xyd entered. To check whether this tableau is optimal, we use this method of multipliers again to see if there will still be an entering variable. Since all the zero values of the decision variables are non-positive, this solution is optimal. Warehouse X supplies supermarket B with 200 units, leaving an excess of 100 units. Warehouse Y supplies supermarket A with 100 units, leaving an excess of 100 units. Warehouse Z supplies supermarket B with 150 units, and supermarket C with 250 units. The total cost for all transactions is 75 pesos times 200, plus 0 pesos times 100, plus 45 pesos times 100, plus 0 pesos times 100, plus 65 pesos times 150, plus 50 pesos times 250 is equal to 41,750. We were able to optimize the starting solution generated by VAM with only one iteration. For practice on the method of multipliers in transportation simplex, try solving the LP using a different starting solution, such as the one generated by the northwest corner method. As a final note, we state that the transportation model can also be used as a maximization problem. Suppose that the cost values in our problem are the savings that the firm earns due to location advantage instead. Naturally, the firm will want to save as much as possible, so what we have now is a maximization problem. Maximize Z is equal to 50xxa plus 75xxb plus 60xxc plus 45xya plus 80xyb plus 70xyc plus 40xza plus 65xzb plus 50xzc. The transportation simplex can only be applied to minimization problems. We first transform our problem to a minimization problem by negating the contribution of each decision variable to the objective function value and treat them as negative costs. Our problem then becomes minimize Z is equal to negative 50xxa minus 75xxb minus 60xxc minus 45xya minus 80xyb minus 70xyc minus 40xza minus 65xzb minus 50xzc. And the corresponding transportation tableau becomes. It is now possible to perform the transportation simplex on this problem. Again, try solving this for more practice.